With the launch of the Parker Solar Probe, interest in solar science is at an all-time high. I'm Tonya Hall for ZDNet and Tech Republic, and joining me is Dr. C. Alex Young. He is a solar astrophysicist, Associate Director for Science at the Heliophysics Science Division at NASA's Goddard Space Flight Center. Welcome, Alex.
Thanks for having me.
Absolutely. So what is your job at Goddard's Heliophysics Science Division?
Well, I wear a lot of hats. One of my jobs is as a scientist. I don't do as much science as I used to do because I have a lot of other things to do. But in particular, I study the sun's activity, a whole area called space weather, which is all of the activity in the sun and how it affects the Earth and other planets. But also I focus very heavily on science communication, how to communicate the science that we do at NASA in the Heliophysics division, at some of the other science groups at NASA, as well as teaching other scientists how to be better science communicators. And I also run a national education program through NASA's Science Mission Directorate that I call the NSEC, the NASA Space Science Education Consortium. And I also do basically marketing for the science that we do in heliophysics, promoting it, supporting it, and helping other scientists and the general public understand better what we do.
How did last summer's solar eclipse help in the preparation for the Parker Solar Probe launch?
Well, first of all, it was a really exciting time. It was the first time that I had been involved in something that big. I actually ran the national program for outreach and engagement for NASA's Science Mission Directorate about the eclipse. And it was a way to share what NASA is doing in science, the solar science, as well as the science we at the time expected to learn about the atmosphere and how the eclipse affected the atmosphere. So it was a time to engage the public, to provide excitement, access, making sure that the whole event was safe for them, for the viewers. And it's something that NASA's never really done on that scale. Probably in some ways, you know, it dwarfed things like the Curiosity landing and the New Horizons flyby and things of that nature. So it was a new frontier for us. It was new territory.
I was in Casper, Wyoming last August with some of the NASA researchers to witness the total eclipse. It was quite moving, and I know there was a lot of data that they were hoping would shed some light. So what did we learn from the eclipse?
Well, there was, as you mentioned, there's a lot of data. There was a lot of science that was done for the eclipse, both in the ground, in the air, on balloons, as well as in space. So, and I would say there are sort of three main areas of focus. There's the science of the solar corona. So that wispy, ethereal outer part of the sun's atmosphere that you only see during a total solar eclipse. That was one area of study, and that was done primarily from the ground and from the air. But also, this was an opportunity to study the atmosphere, and really kind of two parts of the atmosphere: the neutral atmosphere, everything from the atmosphere we live in up to the edges of the stratosphere, as well as something called the ionosphere. So that's the outer part of the Earth's atmosphere, which is actually kind of our interface to space. It's different than the neutral atmosphere because it's made up of something called a plasma. It's electrical in nature, and it's also a gateway for communications. We use it to communicate around the world. We communicate through it, and it's impacted by the sun, and it's impacted by the day and night. And of course, the eclipse was sort of an extreme example of day and night, going from full sunlight to this huge shadow traveling across it. So the solar science is still coming out. There's so much data that's being processed, mostly image and spectral data that's being processed. We have some preliminary results. We were, for example, able to measure types of light, in particular infrared light, from high altitude locations, from airplanes, where there's much less atmosphere, because this infrared light doesn't make it through the atmosphere. Plus, it's much colder up there. And because infrared is heat, you want it to be very cold around you, because all the heat sources around you are basically noise. They overwhelm the signal that you get. But the reason that's important is that we saw some particular, what we call spectral lines. So you look at a spectrum of light, and you will often see peaks at certain wavelengths. And those act as a fingerprint of certain elements in the solar atmosphere. But in this case, those particular spectral lines are sensitive to magnetic fields. Turns out those spectral lines, when there's a magnetic field, split. And the stronger the magnetic field, the stronger the separation between those lines. Their wavelengths shift. And the reason that's important is that the corona is where solar activity occurs. And all that solar activity is primarily driven by magnetic fields from the sun. And we can measure those magnetic fields quite well on lower down in the solar atmosphere, what we call the photosphere, the visible part. But in the corona, where they are driving all of that action, we can't measure them directly. And it's extremely difficult. Well, we can, but it's extremely difficult. And so we're trying to find new ways to do that. So a long story short, turns out those lines that we see during the eclipse in infrared are sensitive and allow us to hopefully start measuring those magnetic fields to tell us about what's going on there.
How important is it for our microcircuit-based society that we understand coronal mass ejections?
It's extremely important. So we are living at the whim of the sun. It provides light, heat, and it is our source of energy that makes us, allows us to wake up every day. But also, it has these outbursts. It has some more long-term continuous outbursts, what's called the solar wind, that's flowing out of the sun all the time, and occasionally has bursts of much faster solar wind. And that can give us something beautiful, the aurora, but it also impacts our ability to communicate. It influences that outer part of the atmosphere I mentioned called the ionosphere. And it disrupts it. It changes the ionosphere. It changes its properties. And so it changes how signals propagate around the Earth or through the ionosphere. But these coronal mass ejections are like a huge tidal wave on top of the solar wind. So they're an extreme burp of solar material, magnetic field, traveling at many, many millions of miles an hour. And when those particles and magnetic field interact with the Earth's magnetosphere, it shakes the magnetosphere. It creates these electrical currents up in the upper atmosphere. And that also changes the ionosphere and disrupts communications. But it also, in the most extreme cases, currents can flow into the ground, but they also look for other ways to flow. And they like to flow in conducting lines, like transmission lines, electrical transmission lines. So if there's a huge current that flows, coming from, created in the upper atmosphere, that now flows through transmission lines, it can overwhelm those transmission lines and cause blackouts. It can knock out the transmission lines. So the other part is that coronal mass ejection, as it's traveling through space, it's pushing stuff ahead of it. It actually has a shock wave. And that shock wave accelerates subatomic particles to near the speed of light. And those subatomic particles create not only a hostile environment for astronauts in space, but they impact our technology. Those particles travel through microcircuits, and they can do what's called bit flipping. So microcircuits are driven by binary codes, zeros and ones, and if those particles travel through them, they can turn a 0 into a 1 or a 1 into a 0 and can cause a great deal of havoc. And then they can even cause charging on the spacecraft much like when you run across a carpeted room in your sock feet and you touch the door at the end of the room and you get a shock. Well, those particles can build up electricity on the spacecraft itself, and it can also discharge. So all of these are electromagnetic phenomena which our technology is sensitive to. So as we become more and more technologically dependent, we become more and more susceptible to all of this influence from the sun.
NASA posted sounds of the sun during vibrations, turning vibrations into sound. What do waves, and you actually narrated that piece for NASA. So what do the waves tell us about the sun?
Well, folks might be very familiar with seismology. So we send sounds into the earth, and then those sound waves travel through different layers of the earth, different densities of material. They come back, bounce back, we measure them, and we can actually, by figuring out the timing and knowing the frequency of that sound, we can look inside the earth and see oil and minerals and structure. Well, something similar can be done on the sun, but the sun actually vibrates naturally. Okay, so inside the sun, it is naturally vibrating at many different frequencies, and those frequencies are bouncing around inside the sun. And when we look at the surface of the sun in visible light, we see tiny oscillations. We see the light flickering because the sun itself is moving. So we can take that light and turn it into signals that allow us to measure those frequencies. And we can do something very similar and look inside the sun. So those oscillations, those wiggles that we see on the sun's surface in light allow us to look inside the sun and see the structure in the sun and do now not Earth-based seismology, but we call it helioseismology, to see rivers of material, to see where magnetic fields are developed, all of this that's happening inside the sun. We can even see sunspots on the other side of the sun using this technique, which is pretty damn cool.
The Parker Solar Probe is going to be launching shortly and collecting data. What are some of the other satellites or probes do we have around the Earth or the sun that might be gathering data?
We have a whole fleet. We have 19 active missions, which are, we call this the Great Heliophysics Observatory. I mean, heliophysics, the study of the sun and its interaction with the solar system, is a system science. It's lots of different systems that are all connected, and so we have to see both the whole and the parts together to see what's going on. So it requires many, many different spacecraft looking at the sun, looking at the space in between the planets, looking at the Earth itself. And so of those, we have many that are looking at the sun. We have spacecraft like SOHO, Stereo spacecraft, Day, Iris. So these are all spacecraft that are specifically looking at the sun or also at some of the space in between. And then we have spacecraft like the MMS spacecraft that's studying the magnetic bubble around the Earth and seeing the interaction of all this stuff coming off the sun, interacting with that and actually causing energy to flow into the Earth environment, giving us aurora, changing the structure of the ionosphere. And we have many other spacecraft that are doing that. But the other thing is that it's very important that all of the other spacecraft that we have that are doing planetary missions have devices to measure the space around them, to measure particles and fields, because all of this environment is created by the sun and its interaction with planets is telling us about this big picture. So all of those instruments and spacecraft around the solar system are measuring different parts of this giant system we call the heliosphere, which is this bubble that sits around the around the solar system, that's created by the sun and its magnetic field as it streams away. So all of those spacecraft are looking at this environment, all the pieces of it, and of course we'll have several missions that will be looking at the sun at the same time Parker is, to help us see the bigger picture and to put what Parker sees into perspective.
You mentioned sunspots earlier. Tell us about sunspot activity cycles. We're in a cycle minimum period right now, right? I mean, how does that affect things on Earth?
Well, so we're in, as you mentioned, we're in a minimum period right now. And so you can kind of think about the sun's magnetic field as going from the one pole to the other. So I've got these little headset on right here. So let's think of it like this. The magnetic field is going, from the North Pole to the South Pole. And as the sun is moving and it rotates, it actually does what's called differential rotation. So it rotates faster at the equator than it does at near the poles. And so those magnetic fields are actually tied to the material in the sun, which is a plasma. It's electromagnetic in nature. And so that means that as the equator moves faster, the magnetic fields near the equator let's see if I can get this to do this, start to bend more. Okay, they're bending faster than what's happening at the north and south. And that starts wrapping up the magnetic field of the sun, twisting it more towards the center than the north and south pole. And those magnetic fields, eventually, you can think of them like rubber bands. They start getting knotted up. Okay, the rubber bands are twisting, the magnetic fields are twisting. Those rubber bands, when they become knotted, they become buoyant, and they float to the surface, and they pop through the surface. And that is a sunspot, where that magnetic field is popping through the surface, the visible surface of the sun. So those magnetic fields, again, like a rubber band, as an analogy, have energy built up in that. You take a rubber band, you keep twisting it, it's going to start knotting. Eventually, it's going to pop. That energy has to go somewhere. You've put so much into it that rubber band will snap. And if you actually were in a cold room and you could measure, you would feel heat around that rubber band where it snapped or where the energy is built up. So the rubber bands or the magnetic fields in the sun do the same or something very similar. They have all of this energy built up in them, and then eventually it has to release. And it releases violently. And that causes particles, material to move around and be heated up on the sun. And when that happens, it creates a huge flash of light. We call that a solar flare. But it also can expel some of that material and magnetic field out into space. We call that a coronal mass ejection. And both that flare and that CME create shock waves, as I mentioned, and they accelerate particles. So those are all of the three things that happen from this violent release of magnetic energy that's happening on the sun. And it's coming from sunspots. That's where that energy is being released. So sunspots, when they're nice and simple and just round, they're uninteresting. They don't have a lot of energy built up. But as they start to become complex and get longer and become more twisted and fragmented, it means they have a lot of energy built up in them. And so when we see sunspots grow, we see them become more complex, we are expecting that they have a stronger potential to erupt. And that's what we see over this cycle. So that twisting of the magnetic field going from sort of straight to very, very twisted back down to straight again takes about 11 years. So we go from low activity to high activity, back down to low activity. And that is the solar activity cycle. And sunspots, you have more of them towards the top and then less of them, or sometimes even none of them when you get towards the minimum, which is the case we have right now.
You know, see, Alex Young, I could talk to you about this forever. What are some of your favorite websites, apps, or online resources to keep track of the sun?
Well, probably one of my favorite ones is one that was made by a colleague of mine here at Goddard called helioviewer.org. So it's really cool because you can go there and you can create videos, you can create images, you can overlay different data, you can take an image of the sun and a coronagraph, which is this artificial eclipse, and you can make your own data sets. And then you can download all of that. So those are really cool, especially looking at things like SDO and SOHO. Let's see, what are some of the other sites I like to go to? There's also one that the Space Weather Group here has developed that has these widgets, and you can actually get about 300 different widgets you can put on your screen with all kinds of different data, and you can monitor space weather. You can go back in time and see what happened, and that's called ISWA, ISWA. I think it's iswa.gsfc.nasa.gov. That's sort of an interactive tool set that they made that's available for everyone. I just go also to the SDO website itself, sdo.gsfc.nasa.gov, to see what's happening on the sun.
So what's one big find that you hope that the Parker Solar Probe will actually discover?
Well, one of the coolest things is the coronal heating problem. So what we think that there's maybe two different mechanisms that are heating the corona. Why does the sun go from the visible surface, which is about 10,000 degrees, up to millions of degrees when you get to the outer atmosphere of the corona? You know, it doesn't really make sense. The inside of the sun is incredibly hot. It's more than, it's more than tens of millions of degrees. And as you move away, it gets cooler, which is what you expect. And then all of a sudden, it gets hot again. That's just really weird. It's just really weird. And so that's the coronal heating problem. Why is the corona hot? And we think maybe it's lots of little tiny flares that are happening, so small that you can't see them individually. We call those nano flares. And actually, Eugene Parker was one of the people that pioneered the beginnings of the research in that area. And all of that energy that's been flowing into the corona and heating it up causes the solar wind to expand away and then expand at supersonic speeds, millions of miles an hour, which is another part of what Parker has been, has led to fundamental research and actually predicted the solar wind in the first place. So if we can really pin down the mechanism for why is this happening, is it really these little micro flares that are going off, or is it some other kind of wave mechanism that's in the corona, or is it a combination of both of those, which is also very possible. So I think if Parker can really nail that down, then we will have a fundamental piece of not only understanding our star, the sun, but all other stars in the universe, and that's pretty cool.
Yeah. I really do appreciate your time, Dr. C. Alex Young. If somebody wants to connect with you, maybe they want to ask you more questions, how can they do that?
Well, probably the easiest way would be to send me a tweet at The Sun Today.
There you go.
And I'm sorry we didn't get to talk more about the eclipse science, because I didn't want the impression to be that there isn't a lot of science that we learned. Actually, one of the areas that's really cool is what we learned about the ionosphere. So when that big shadow moved across the Earth and changed the atmosphere, it was moving at thousands of miles an hour, it actually changed the atmosphere in pretty cool ways very quickly. And we learned a lot about our atmosphere. We learned a lot about the ionosphere and actually saw things that had been predicted for 50 years, and we really saw them for the first time. So there's a lot of cool stuff. You said I could go ahead and mention this. I will mention that I wrote up some of this, and there's way more than I could even put in an 8-page article, but I wrote an article in Sky and Telescope, which is going to come out in the August edition, so just a couple of days from now.
Well, very exciting. We'll be looking for that, and we'll just have to have you back to talk more about the eclipse.
I would love to talk more about the eclipse, more about the sun, stars, and space in general.
Thanks again. And if you guys want to find more of my interviews, you can do that right here on ZDNet or Tech Republic, or maybe go to my website, tonyahall.net. I have links to all my social sites, including Twitter, at Tonya Hall Radio on Twitter. Connect with me. I want to hear from you. Thanks for watching.